China has built the most complex skyscrapers ever designed. And this isn't about height. This is about 18 towers scattered across the country that broke every rule. Architects and engineers thought was permanent buildings that twist, lean, loop, and cantilever in ways that weren't supposed to be possible at this scale. China now has over 3,500 skyscrapers, more than the next 11 countries combined. You heard that right. One country has more high-rises than the United States, the UAE, South Korea, Japan, Malaysia, Australia, Indonesia, Canada, the Philippines, Thailand, and India put together. And among all of those towers, the 18 you're about to see didn't just go tall, they went structurally insane. And it starts with a building in Beijing that wasn't even designed to stand up straight. Defying geometry, structures that shouldn't stand. You're looking at a building in Beijing, and the first thing your brain does is reject it. 2 towers, each leaning at 6 degrees off vertical, rising over 760 feet into the sky and then 36 stories above the ground. They bend toward each other and connect through a massive cantilevered bridge that juts out 245 feet from one side and 220 feet from the other. That's the CCTV Headquarters. Designed by Rem Koolhaas and the Office for Metropolitan Architecture, with engineering by Arup, this isn't a skyscraper in any traditional sense. It's a continuous loop, a 3-dimensional cranked tube of steel and glass that folds back on itself like some kind of architectural Mobius strip. The entire building is wrapped in a diagrid exoskeleton, a web of triangulated steel braces where the pattern gets denser, where the stress is highest, and loosens where the load is lighter. You're literally reading the building's structural forces on its skin. Over 125,000 tons of steel went into this thing. And because it sits in one of Beijing's most active seismic zones, Arup had to run advanced nonlinear simulations on all 40,000 structural elements just to prove it wouldn't collapse in an earthquake. But here's the detail that most people miss. When the 2 leaning towers were finally joined at the top, the engineers had to wait for the coldest hour of the night before sunrise. When both towers had cooled to the exact same temperature so that thermal expansion wouldn't lock stress differentials into the connection. One wrong calculation, and the entire structure could have buckled under its own geometry. But the CCTV Headquarters wasn't the only Chinese tower built to defy the way gravity is supposed to work. Over in Guangzhou, the Canton Tower takes a completely different approach to structural insanity. Standing nearly 2,000 feet tall, this is a hyperboloid lattice structure, essentially 2 ellipses, one at the base and one at the top, rotated in opposite directions and connected by 24 steel columns that twist as they rise. The result is a tower that narrows dramatically at its waist, just about 100 feet across at the tightest point, before flaring back out toward the top. And that twist isn't decorative. It's the structure. The rotation stiffens the tower against lateral wind loads, the same way twisting a rope makes it stronger. But a tower this slender at nearly 2,000 feet is dangerously vulnerable to sway. So the engineers installed a hybrid mass damper system, 2 650-ton water tanks working in sync with motorized active dampers that respond to the building's movement in real time. Over 40,000 tons of structural steel hold the whole thing together, and not a single one of the tower's 1,100 steel nodes is identical to any other. Every joint, every connection, every angle is unique, a 3-dimensional puzzle with over 3,000 completely custom pieces. Then you move east to Suzhou, where the gate to the east takes the concept of a connected tower and pushes it even further. Designed by RMJM, this is a super tall that rises nearly 1,000 feet as 2 curving towers that separate above a 7-story podium, arc outward to form a monumental void, and then reconnect at the top through a massive structural arch. A belt truss wraps the full perimeter where the 2 legs merge, and the whole thing sits directly above an active underground rail interchange that's fully integrated into the building's foundation. The engineering challenge here isn't just the arch. It's that the columns flanking the void have to taper inward above the podium while still transferring enormous gravity loads through an irregular path down to the base. You're asking steel and concrete to do something they weren't designed to do, carry the weight of a super tall through a shape that looks like it belongs in a Roman aqueduct, not a central business district. And then there's the Grand Lisboa in Macau, a tower that doesn't just lean or twist, but blooms. Designed by Dennis Lau and Chun Man, this 52-story structure rises about 850 feet into the sky in the shape of a lotus flower. The upper floors cantilever outward on multiple sides by more than 65 feet each, which means the building actually gets wider as it gets taller. That's the exact opposite of what most skyscrapers do. The podium at the base is an elliptical dome, a thin shell structure braced by a skeletal frame housing one of the largest casino floors in Asia. And because Macau sits in a typhoon corridor, the entire structure had to be engineered to withstand extreme lateral wind loads, hitting an increasingly exposed surface area the higher you go. The facade alone uses more than 5,600 panels of glass, coated with a thin layer of gold, arranged in patterns inspired by Fabergé eggs. 3 billion Macanese patakas, and roughly 3 years of construction later, the Grand Lisboa became the tallest building in the territory, and one of the most structurally unconventional casino towers ever built. But bending geometry is only the beginning, because the next group of towers didn't just reject straight lines, they rejected the very idea of a building having the same shape on every floor, twisted in parametric, where no two floors are the same. If the buildings you just learned about rejected straight lines, the Shanghai Tower rejected the entire concept of repetition. Standing 2,073 feet tall, 128 stories, this is the tallest building in China and the third tallest on the planet. Designed by Gensler, the tower's outer glass facade completes a full 120-degree rotation as it climbs from the ground to the crown. And that twist isn't there to look impressive on a skyline. It's there because typhoons off the East China Sea would otherwise tear the building apart. Wind tunnel testing proved that the spiraling form reduces wind forces on the structure by 24% compared to a conventional rectangular tower. That single design decision saved $58 million in steel alone. You heard that right. Just the shape of the building cut its materials bill by a quarter, underneath the twisting skin. The structure runs on a mega column and outrigger system, a 90 by 90 foot reinforced concrete core connected to super columns through massive outrigger trusses that stiffen the whole frame against lateral loads. At the top sits an 1,100-ton tuned mass damper, a pendulum-like counterweight that swings opposite to the building's sway during high winds. And because Shanghai sits on soft silt, the foundation alone required over 1,000 bore piles driven 85 meters deep into the earth. Anchored by one of the longest continuous concrete pours in modern super-tall history. 9 cylindrical zones are stacked on top of each other inside the double-skin facade, each one functioning like its own neighborhood with its own sky lobby, its own gardens, its own climate system. This isn't a skyscraper. It's a vertical city wrapped in a glass corkscrew. But if the Shanghai Tower redefined what a super-tall could be, the Leeza SOHO Tower in Beijing redefined what a building could be forced to become. Designed by Zaha Hadid architects, Leeza SOHO rises 45 stories in Beijing's Fangtai business district, and it exists in 2 halves. That's not a metaphor. The site is diagonally sliced by an active subway tunnel running between lines 14 and 16 of Beijing's underground network. The architects couldn't put foundations on top of the tunnel, so they split the tower down the middle 2 separate structural cores, one on each side, enclosed within a single facade shell. And where those 2 halves separate, a void opens up. That void runs the full height of the building and twists 45 degrees as it rises, creating the world's tallest atrium at 194 meters, over 630 feet of open air, spiraling through the core of a skyscraper. 4 sky bridges connect the 2 halves at different levels, and the atrium itself functions as a thermal chimney, pulling air through an integrated ventilation system that filters Beijing's notoriously polluted atmosphere. The whole thing was built in under 5 years, from groundbreaking in 2015 to opening in 2019. And it was one of the last major projects Zaha Hadid personally designed before her death in 2016. Then there's the Greenland Hangzhou Century Center, a project that took the Twin Tower concept and turned it into something that looks less like a building and more like a letter of the alphabet dropped onto a riverbank. Designed by Skidmore, Owings, and Merrill, this complex consists of 2 super-tall towers, each rising over 990 feet. 64 floors that curve toward each other and connect through a sweeping 6-arch steel sky bridge suspended over 100 feet above the ground. The shape is derived from the letter H for Hangzhou, but the engineering beneath that symbolism is anything but ornamental. Each tower integrates a reinforced concrete core that transitions from an octagonal shape to a rectangular one as it rises, resisting lateral loads from both wind and seismic activity. The floor plans taper upward to reduce vortex shedding, and the sky bridge itself was designed using funicular principles to minimize bending forces across its 60-meter span. Above it, a suspended drape roof made of bidirectional steel grids follows a catenary curve, the same shape a chain makes when it hangs under its own weight, engineered to transfer loads as efficiently as possible through pure axial force. Over 530,000 square meters of total floor area, offices, a 5-star hotel, residences, and a boutique shopping complex, all inside a structure that looks like it's dancing. And in Hefei, the Feiqui Tower, also known as the Anhui Broadcasting and TV Center, adds a layer of complexity that has nothing to do with height and everything to do with surface, rising around 245 meters with a spiraling scroll-like form. The tower's entire facade is inscribed with ancient Chinese seal script, characters from a calligraphy tradition over 2,000 years old, carved into the skin of a modern high-rise. But the real engineering challenge isn't the lettering. It's the underlying geometry. The tower's gently twisting form means that no two floors share the same footprint, and the facade panels had to be individually modeled using parametric software to maintain visual coherence across a surface that never repeats. Every panel is custom, every curve is calculated. And the result is a building that functions simultaneously as a broadcast headquarters and a cultural monument, proving that parametric design in China isn't just about pushing form, but about encoding identity into structure. But twisting towers are only part of the story. Because the next wave of Chinese skyscrapers didn't just twist, they reached heights that demanded engineering systems most countries have never attempted. Megatall engineering, the towers that demanded new structural science. At 599 meters, 1,965 feet, the Ping An Finance Center in Shenzhen is the 4th tallest building on the planet, and it was supposed to be taller. The original design by Kohn Pedersen Fox included a 60-meter spire that would have pushed the tower past 660 meters. But in 2015, the spire was removed over concerns that it would interfere with nearby flight paths. So the building you see today is, in a sense, an amputated version of itself, and it's still nearly 2,000 feet tall. The structural system holding it up is a tube-in-tube configuration, a massive composite concrete core at the center, connected to 8 megacolumns on the perimeter through 5 outrigger trusses and 7 belt trusses. Those megacolumns aren't hidden inside the walls. You can see them chevron-shaped stone panels running the full height of the tower, flaring outward at the base and converging at the crown. The tapered form reduces baseline wind loads by 35%, and the facade is clad in 1,700 tons of marine-grade stainless steel, the largest application of stainless steel on any building facade in the world, chosen specifically because Shenzhen's salty coastal crest. Air would corrode anything less durable within a decade. 428 sensors are embedded throughout the structure, collecting real-time data on wind pressure, seismic movement, and structural stress from the day construction began through the rest of the building's life. This isn't just a skyscraper, it's a building that monitors its own skeleton. But the Ping An Finance Center had one advantage. Most super talls share it gets narrower as it rises. The CCTV Tower in Beijing does the exact opposite. Also designed by KPF, this 108-story tower stands 528 meters tall and takes its shape from a zun, an ancient Chinese ceremonial wine vessel from the Bronze Age. In profile, the tower is wide at the base, narrows to a 54-meter waist at the middle, and then flares back out to 69 meters at the top. That means the heaviest, widest part of the building is at the crown, the exact place where you want the least mass if you're trying to keep a super tall stable in high winds and earthquakes. And Beijing sits in one of China's highest seismic zones, so Arup, the structural engineer, had to design a system that could handle enormous lateral forces while carrying extra weight at the top. The solution was a megaframe, concrete-filled steel tube megacolumns at the perimeter, paired with mega braces and belt trusses, all anchored to a reinforced concrete core embedded with steel plate shear walls. Parametric modeling was used to optimize every structural member in the perimeter system, testing thousands of configurations to find the most efficient layout. The entire design was verified through shaking table tests, physical models subjected to simulated earthquake forces, and nonlinear time history analysis that modeled how the building would behave second by second during a model field formation. Major seismic event. Construction took 62 months from groundbreaking to topping out 1.4 times faster than comparable supertalls anywhere in the world. And because the tower sits at the heart of Beijing's central business district, the entire build had to happen without disrupting 4 subway lines and a pedestrian tunnel network running directly beneath the site. Then there's the Jinmao Tower in Shanghai, the building that started everything. Completed in 1999, this 88-story tower, designed by Skidmore, Owings, and Merrill, was one of the first supertalls ever built in Pudong, long before the Shanghai Tower or the World Financial Center existed beside it. At just over 1,400 feet, its form is a modern reinterpretation of the Chinese pagoda, a series of graduated setbacks that echo the tiered silhouette of traditional temple architecture. But underneath that cultural reference is a brutally efficient composite structure. An octagonal reinforced concrete core surrounded by 8 composite supercolumns, connected through outrigger trusses at 3 levels. This was the structural template that would go on to influence nearly every supertall built in China over the next 2 decades. The Jinmao Tower proved that Chinese construction could deliver world-class engineering at supertall heights, and it did so at a time when most of the world still thought of Shanghai as a city of low-rise riverfront. Buildings. Right next to it stands the Shanghai World Financial Center, 492 meters tall, designed by KPF, and famous for the trapezoidal aperture cut through the top of the building. That opening wasn't just an aesthetic choice. It was originally designed as a circle, but was later redesigned into a trapezoid to reduce wind vortex shedding at extreme heights, the phenomenon where wind flowing around a building creates alternating low-pressure zones that cause the structure to sway. The diagonal mega-bracing system and 3-story-high outrigger trusses make this one of the stiffest supertalls ever built relative to its height. And the aperture itself became one of the most recognizable architectural features in Asia, a functional engineering solution that turned into a global icon. And then you get to the Chongqing Chaotianmen, the project that stopped pretending a skyscraper has to be vertical at all. Designed by Moshe Safdie, the Raffles City complex consists of 8 towers, 4 of which are connected at 250 meters above the ground by a horizontal skyscraper called the Crystal. This thing stretches 300 meters long, roughly the same length as the Eiffel Tower is tall. The Crystal weighs 12,000 tons of continuous steel, and its 3 middle segments, each weighing up to 1,100 tons, had to be hoisted individually to their final position at height. That lift was a world first. No one had ever raised prefabricated steel sections of that mass to that altitude on a building before. Inside the Crystal, you'll find pools, gardens with 9-meter-tall trees, restaurants, an observation deck with a glass floor, and an outdoor sky park. Below it, the 8 towers contain shopping malls, luxury residences, offices, serviced apartments, and a hotel. Over 900,000 people showed up on opening weekend. This is not a building. This is a city, suspended in the air, bolted to 4 towers, hovering over the confluence of the Yangtze and Jialing rivers. But even vertical cities need to breathe. And the next group of towers figured out how to make skyscrapers not just structurally complex, but environmentally intelligent. Sustainability, facades, and the architecture of intelligence. In Guangzhou, the Pearl River Tower proved that a skyscraper could actually fight back against the climate it was built in. Designed by Skidmore, Owings and Merrill with Adrian Smith and Gordon Gill as lead architects, this 71-story tower was engineered from the ground up to approach net zero energy consumption, a goal almost unheard of at super tall scale. The building's curvilinear form wasn't sculpted for aesthetics. It was shaped through computational fluid dynamics to funnel prevailing winds into venturi openings cut through the mechanical floors, where vertical axis wind turbines convert that accelerated airflow into electricity. The aerodynamic shaping effectively doubles the wind speed at the turbine inlets, amplifying energy output 8-fold compared to a freestanding turbine. A double-skin facade wraps the broad faces of the tower. The outer layer allows controlled solar heat in, while the inner layer blocks solar gain, creating a ventilation corridor between the two skins that passively regulates the building's internal temperature. The offices are cooled through radiant ceiling panels and chilled beams instead of conventional ductwork, which freed up so much vertical space that the design team added 5 extra floors to the building without increasing its overall height. Solar collectors are integrated directly into the facade, and the result is a tower that uses roughly 58% less energy than a comparable conventional building. The Pearl River Tower didn't just set a benchmark, it rewrote what energy efficiency means at 300 meters. But not every breakthrough in Chinese skyscraper design is about sustainability. Some of it is about turning a skyline into a painting. That's what Mad Architects did with Chaoyang Park Plaza in Beijing. This 10-building complex sits on the edge of the city's largest remaining park and was designed to look like a traditional Chinese Shanshui ink landscape, translated into built form. The twin office towers rise as asymmetrical mountain peaks, their glass facades carved with deep ridges and valleys that mimic the erosion lines of ancient cliffs. The vertical fins running up the exterior function as an energy-efficient ventilation and filtration system, pulling fresh air in while filtering out Beijing's particulate-heavy atmosphere. A reflective pond at the base doubles as a passive cooling system, lowering ambient temperature during the brutal summer months. The low-rise buildings scattered between the towers are shaped like eroded river stones, and the landscape weaves pine trees, bamboo, rocks, and water features drawn from classical Eastern garden design. LEED Gold certified. This project is both environmental infrastructure and cultural statement proof that parametric forms in China don't have to choose between performance and poetry. And the ambition keeps compounding. The China Resources Headquarters in Shenzhen uses a faceted crystalline geometry, where the building appears to shift shape depending on where you're standing. A non-orthogonal curtain wall requiring custom structural solutions at every level. The Tianfu Twin Towers in Chengdu connect 2 supertalls with a habitable sky bridge, engineered to handle differential movement between the towers caused by wind and thermal expansion. And the Hangzhou Wangchao Center Tower, designed by SOM as both architect and structural engineer, rises 280 meters in a dramatic undulating curve inspired by the rolling T-hills of Zhejiang province, with every floor plate shaped differently to follow the building's sinuous profile, demanding parametric facade modeling and custom MEP coordination from foundation to crown. These aren't just buildings. These are systems, structural, environmental, and cultural, compressed into vertical form and pushed to the edge of what current engineering can deliver. 18 towers, 1 country, and every single one of them proof that when it comes to the most complex skyscrapers ever designed, China isn't competing with the rest of the world. It's the rest of the world that's trying to keep up.